Hello, everyone. Welcome to the April Green Chemistry Connections. Thank you all for joining us today. Today we have a wonderful topic of systems thinking, sustainability, and circularity teaching tools. And we have a wonderful lineup of speakers that we're excited to hear about. So we'll just get started with some housekeeping things before we do that. So first of all, introduction. So my name is Gagan. I'm a PhD student here at McGill University in Montreal, Canada.
I'm Sarah. I'm also a PhD student at McGill University in Canada, also one of the co-organizers.
And I am Jasmine Hong. I am the third PhD student from McGill University, also in Montreal. I'm excited to join you all here today. We also have two other co-organizers who aren't with us today as they handle the Australian connections, but they are Tessa Falks and Adele Mastroyanis from Monash University and Flinders University in Australia, respectively.
So hi, everyone. I'm one of the ambassadors for this year's webinar series. My name is Sarah, and I'm a PhD candidate at Memorial University of Newfoundland, so specifically to St. John's campus on the far east coast of Canada.
Hi everyone, I'm Michelle. I'm also an ambassador for this year. I'm a PhD candidate at Carleton University in Montreal.
So before we get started, we just want to thank our sponsors, Millipore Sigma and ICL. We wouldn't be able to hold these webinars without their support. And we also wanted to start with some land acknowledgements. So again, a number of us are based in McGill University in Montreal, so I'll just read the land acknowledgement. So McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. McGill honors, recognizes, and represents and respects these nations as the traditional stewards of the lands and waters on which we meet today.
We would like to begin by acknowledging that Concordia University is located on unceded Indigenous land. The Kanien'kehá:ka Nation is recognized as the custodians of the lands and waters on which we gather today. Tiohtià:ke Montreal is historically known as a gathering place for many First Nations. Today, it is home to a diverse population of Indigenous and other peoples. We respect the continued connections with the past, present, and future in our ongoing relationship with Indigenous and other peoples within the Montreal community.
Being based out of Newfoundland, we'd also like to acknowledge that the lands on which Memorial University's campuses are situated are in the traditional territories of diverse Indigenous groups, and we acknowledge with respect the diverse histories and cultures of the Beothuk, Mi'kmaq, Innu, and Inuit of this province.
Okay, sorry about that. So just to go over some logistics for the Zoom, please add your pronouns to your display name. So you can do that by clicking the rename menu from the dropdown. And this is just so we can address everybody in the way they identify and be respectful to one another. Additionally, you can enable the live transcripts at the bottom, clicking the CC button at the bottom of your screen. Lastly, the slides and transcripts will be made available after the connections as well.
So we do also have a code of conduct for these green chemistry connections. Not only are we going to hear a few wonderful speakers speak today, but we will also be having breakout rooms. So just kind of addressing the behavior for that. So at Beyond Benign events, we want everyone to feel welcome and included. By participating, you agree to treat all attendees with respect, regardless of their identities. Discrimination or harassment of any kind will not be tolerated. There are no consequences for reporting inappropriate behaviors. Beyond Benign reserves the right to determine what constitutes inappropriate behavior or unfair treatment and will take appropriate action as needed. Thank you for helping us create a safe and supportive environment for all. And when we do the breakout rooms, the general guideline is to speak up, introduce yourself, then step back and give others the space to speak about themselves.
So to just briefly go over today's agenda, we have an excellent lineup of 4 incredible speakers today. So obviously we just did the welcome and introduction, and then we'll be leading into our first set of talks from Professor Peter Mahaffy and Alisha Szozda, who will be presenting work from the IUPAC group on systems thinking, sustainability, and known as SASTIS, I believe. Following this, there'll be a Q&A with both Peter and Alisha, and then there'll be a short break. And after the break, we will have talks from Dr. John Beatty from the Texas Women's University and Christina Griever-Wilson from My Green Lab. So to jump into our first round of introductions. So Peter Mahaffy is a 3M National Teaching Fellow, professor of chemistry at King's University in Edmonton, Canada, and director of the King's Center for Visualization in Science, which provides digital learning resources used by a half million students, educators, and the public from over 100 countries each year. His current research and professional work is at the interfaces of chemistry education, systems thinking, and sustainability, the uses of interactive visualization tools to facilitate the learning of science, and the responsible uses of chemistry. Mahaffy served for 6 years as the chair of the IUPAC Committee on Chemistry Education and as a member of the IUPAC Bureau. He is presently co-chair of several IUPAC projects on systems thinking and sustainability in chemistry and a titular member of the IUPAC Committee on Ethics, Diversity, Equity, and Inclusion. His work has been recognized with national and international awards from the Chemistry Institute of Canada, the College Chemistry Canada, and the American Chemical Society and IUPAC. In March 2025, he received the ACS George C. Pimentel Award for Outstanding Contributions to Chemistry Education.
And we additionally have Dr. Alisha Szozda, who completed the concurrent education program at Queen's University to obtain an HBSc in chemistry in 2018 and a B.Ed in 2019. Due to her passion for education and research, she completed a PhD in chemistry, specializing in chemistry education research at the University of Ottawa with Dr. Alisha Flynn. Her research focuses on investigating systems thinking in chemistry education, educators and students' perspectives and experiences that were funded through the SSHRC Canadian Doctoral Scholarship. During this time, Alisha joined the IUPAC Systems Thinking in Chemistry for Sustainability toward 2030 and Beyond project, where she has co-created open educational resources on a website for people to learn about systems thinking and how to implement it in chemistry education. She is passionate about teaching and currently embeds green chemistry and sustainability principles and systems thinking into a chemistry for engineers course at Carleton University. As of March 2025, she has started a new doctoral fellowship role at Carleton University focusing on EDI transformation in STEM and has joined Beyond Benign as a chief moderator for the GCTLC. She will bring her strong passion for green chemistry education and abilities to lead and develop community engagement and activities within the educational communities as this role at Beyond Benign. Alisha currently lives in Ottawa, Ontario, where outside of work, they enjoy hot yoga and fitness classes, long dog walks, kayaking, Jordan Bay, skiing on the Gatineau Hills, and exploring different places to eat. So welcome these two for their presentation today.
Okay, so there we go. We can see the screen being shared. Thank you for the wonderful introduction, everyone. And it's such a pleasure to be and privilege to be here speaking to you all about sustainability and systems thinking in chemistry education. I'll be co-presenting with Dr. Peter Mahaffy. And so we've already kind of done some introductions, but I'll let us just give a little bit more. So Peter, do you want to take it away?
Sure. Thank you very much. And it is truly a privilege to be here. I'm a big fan of what Beyond Benign has done and the Green Chemistry Institute at ACS. So it's a privilege to be here. Jasmine said it all about the King Center for Visualization in Science, but if you just click the next slide, Alisha, there we go. So I just wanted to acknowledge the team that worked last year. It's a team of undergraduate students, one faculty member in physics, and I mention them now because a number of the resources that we're going to be showing today were created by the team. And if you're interested in these at all, just make a note of kcds.ca where you can go to see more.
So thanks, Peter. And so my I have a slide here to share a bit of my educational journey, but it was really outlined nicely in the introduction. So I'll briefly just say that, you know, a lot of my green chemistry and system thinking knowledge came from my PhD at the University of Ottawa with Dr. Alison Flynn. And specifically my research was on systems thinking, which is how I got to meet Peter. I was fortunate enough to meet Peter as he's a collaborator on that project. So later on, you know, that led to me being a member of the UPAC project on systems thinking, and so where I am today has really been shaped based off of these experiences. You know, that's where, you know, I'll talk a little bit later about, you know, how I've been integrating green chemistry principles and systems thinking in the chemistry for engineers, starting a postdoctoral fellowship, and then again, I'm very honored to be part of the Beyond Benign community as the chief moderator of green chemistry, of the green chemistry teaching and learning community. So, and there's lots of fun things happening there. So these roles and experiences that I share can kind of help situate how I've developed the knowledge and resources that I'll be sharing with you today. But before we do that, we want to get to know a little bit more about you. So can you please go to menti.com, and you can either enter this code or you can just scan this QR code to join. And there's a few questions. So the first question, and I can also share this screen. There we go. So we want to know a little bit if you teach students, and maybe you don't, and you can add comments on the Menti question to share if where you're coming in from, what's your role or your current roles. We want a little bit about you, and that will help kind of shape what we're talking about today. So how many are there? 38 participants. Oh, cool. And I'll unhide the responses in a sec. It's always fun to see kind of all the bubbles appear after we get the responses in. So I'll wait a few more seconds to put in your answer. Okay, so shall we reveal, Peter?
That sounds good.
Okay. There we go. Okay, so majority saying we don't teach. Interesting. That's great to know. Teach second year plus, higher ed first year, got some high school grade 8 to 12. That's great. Okay, so the next question is, if you do teach, and this might not be applicable based off of the last question, but what do you teach? Give you a few seconds to answer that in the Menti pool. Okay, let's see. Okay, so majority saying chemistry. Makes sense with that. We don't align with those that don't teach. Okay, another science discipline. Interesting. That's great. Okay, so and we can see kind of like the the relationship from that last question. So K to grade 8 or higher ed, teaching chemistry, grade 8 to 12. Interesting. This is great. Thanks for participating. And we have one more question, which is related to this talk. And we want to know, what is your current knowledge and experience with systems thinking? So this is rating your experience of the 5 items from a strongly disagree to strongly agree scale. Fun. I like this comment feature. It's great. And this one will take a little bit more time, so I'll give you a few more seconds to do that. Okay, let's see, let's reveal the responses. Okay, so this is what the results say. So some of you have heard, looks like a good portion of the audience has heard of systems thinking before. That's great. Heard of systems thinking being used in the discipline. It's kind of scattered across this scale. That's interesting. Have you used a system mapping tool? Okay, so majority saying no. Well, you'll learn about some tools today, which will be exciting. Have developed a system thinking activity? No. And implementing. Okay, so it looks like we have some knowledge, but not so much experience. And so that is great to know, because there's some tools that we'll be sharing today that can help with that implementation part. Okay, so I think, Peter, now I'm going to stop sharing and you can start sharing the slides.
Trying to make sure I'm sharing the right screen here. I transitioned to Teams with great reluctance from Zoom after COVID, and here we go. Let's see here. Advanced sharing options. No, it will not seem to let me share the right screen. Let me just try that again.
And if not, I can share on my end too. Oh, I think that's working now.
But it's
Yeah.
it's giving me the wrong screen. All right, sorry, we checked the tech out beforehand, but this was something that was working last night. Let me just see here. Okay, well, no problem. I will just slide everything over to the other screen. Give me just a second. Here we go. Let's try this. Technology is great when it works. Yeah, I think we're getting there. Let's see here. There we go.
There you go.
You're seeing it now? Okay. Sorry for that delay. Let me just get to the right place in talk here. Here we go. So our title is about sustainability and systems thinking in chemistry education. And we thought a good place to start might be with just what is our sustainability challenge? What is the state of our planet? And one of the things that describes pretty well the state of our planet right now is a word that's not yet in the Oxford English Dictionary called polycrisis. Multiple interconnected crises converge, they amplify each other, predicaments that are difficult to manage or resolve. And this is a term used a lot by the World Economic Forum. Every year, they go to global leaders around the world and say, what are the biggest risks you anticipate our world facing, your country facing in the next 2 years? And they break these down by sectors: economic, environmental, geopolitical, societal, technological. And so here's what the global leaders said in January. This was I think this poll was taken, it was published in January, taken right before we had an administration change in a country, and it might be a little bit different now. But the short term is interesting in comparison with the long term. And by the time we get to what are the global risks ranked by severity over the next 10 years, now 4 of the top 5 have to do with things related to the sustainability of our planet. And so we're talking about systems thinking and sustainability, and the World Economic Forum connects those dots with a system map. They call it an interconnections map. And it won't be a surprise to you that risks that happen, for instance, in Earth systems, critical change to Earth systems, those are related to societal polarization, to misinformation and disinformation, and so on. We'll be looking more at system maps later today. Another measure of the environmental challenges with respect to the state of our planet comes in a bioscience report every year. And the last one published is the 2024 State of the Climate Report. 25 of 35 planetary vital signs are at record extremes. And these won't be surprising to you, but when you put 5 of them together, they tell a really profound story. So what we're looking at up on the top is world ocean sea surface temperature anomalies, data for the last 30 years shown in the gray lines, and then we have 2023 in blue and 2024 in red, just far exceeding the means from the previous 30 years. Or the North Atlantic Ocean sea surface temperature, global sea ice extent, now 2023 and 2024 are at the bottom, also in the Antarctic. And then world surface air temperature, one of the most important measures of how our climate is doing. And in addition to these parameters changing because of geopolitical changes in various places in our planet, we actually have sustainability signposts that are disappearing from both our headlines and consciousness. So the agencies that track parameters like this are also facing very perilous times. And that's just a huge concern for those of us who care about sustainability. Sustainability has been called the 21st century's biggest challenge. An editorial in Nature a couple of years ago asks, why are world leaders ignoring sustainability? And I suppose if that editorial were to be written today, it might be, why are world leaders undermining and sabotaging sustainability? So these are active acts to try to undermine sustainability. But chemistry, the discipline that focuses on the flow of matter and energy, the transformation of matter on our planet, it plays a central role in the emergence of sustainability. In order for that to be realized, education in and about chemistry needs to be reimagined. And another editorial in Nature suggests that this needs to be done with systems thinking. And so global voices are calling for systems thinking to tackle complex sustainability challenges. The International Science Council, we need new approaches to tackle climate change, complex sustainability questions. The World Economic Forum has just published a very interesting report, not only on the great potential for systems thinking in education, but suggesting that this is an essential skill for a sustainable future. And they outline some very interesting ways to try to implement systems thinking across the curriculum. Chemistry is behind. And IUPAC tackled that. I've been very involved with the International Union of Pure Applied Chemistry for several decades. And we decided to tackle that along with the International Organization of Chemical Sciences and Development, and with really strong participation from the ACS Green Chemistry Institute. With launching a project initially in 2017, we invited about 20 global thought leaders in chemistry and chemistry education to come together on a 3-year project and think about systems thinking, which is so important in some disciplines, but really unknown in chemistry education. How might it apply to chemistry education? How can that help the next generation address emerging global challenges? And I think we asked 20 people and 20 people said yes. And these were very busy people. So it's an indication that the community is aware that this really needs to be done. We started doing an extensive literature search on systems thinking in STEM disciplines and systems thinking in chemistry education. And the number of publications there were in 2017 on systems thinking in chemistry education was 0. And so after a literature search, working for 2 or 3 years to begin to tease out what this might look like, do some beginning of research about effectiveness of systems thinking in chemistry education, there were a couple of important outcomes, one which you may be familiar with. Some of you in the room are co-authors in a special issue in December 2019 of the Journal of Chemical Education, Reimagining Chemistry Education, Systems Thinking, and Green and Sustainable Chemistry. We followed that up at the end of that project with a second project, which is really the basis for what we're talking about today, systems thinking in chemistry for sustainability toward 2030 and beyond. And this project has 3 strands, one of which is focused on systems thinking in chemistry education, continuing that work. One was focused very much on trying to put chemistry in the spotlight when it comes to sustainability science. And so we had a project for the International Year of Basic Sciences for Sustainable Development. I'll show you one of the outputs of that. And the third strand was to begin to ask chemical industry in a more formal way. Can we think about the extent to which chemical industry does systems thinking and the extent to which chemical industry leaders are interested in pursuing that further? Now, this came right during COVID, and chemical industry was, I think, completely preoccupied with things like supply chain management and so on. And after COVID, coming back to our industrial partners, I think there was a strong appreciation for the fact that, well, we have supply chain issues during COVID because we could do systems thinking better. And so we now have 12 thought leaders at pretty high levels in chemical industry around the world who are just starting a project working on systems thinking, sustainability, and the chemical industry. And we're very excited about that project. Turn it over to you, Alisha.
Great. So Peter has done a great job of outlining kind of the need for systems thinking, but what is it? And so here we created a working definition of systems thinking, which involves both analytical and holistic thinking, such as identifying and examining system components, their organization, causal factors, and system boundaries, as well as describing and interpreting system level behaviors in interactions of the system with its environment. So in this work, we decided to break this down into 4 components to tackle different components of systems thinking. And so students can engage in systems thinking skills to identify and analyze the composition of a system. So those include the components and boundaries, its structures, the interactions between the organization of components. It could be look at their system behaviors, so the behaviors that from interactions between the components in its environment, and the effects of a system of interest, including the intended and unintended consequences. And so other disciplines have been implementing and investigating systems thinking, such as biology, engineering, and geoscience. And several papers have reported on the proposed benefits of systems thinking, showing the potential for its use in chemistry education. And so over the last couple of years, research has investigated students and educators' experiences and perspectives of a systems thinking approach in chemistry education. And so these several benefits include, sorry, I got ahead of myself here. These benefits from the other disciplines include promoting learning of content more deeply and conceptually, and improving problem solving and critical thinking abilities, and preparing students to understand and address complex real world problems to promote planetary sustainability. So to know if these benefits are applicable to chemistry education, research
in progress
needs to be conducted. And so this is where over the last couple of years, research has investigated students' experiences and perspectives of a systems thinking approach in chemistry education. And so several benefits have reported from these studies, which include systems thinking may be beneficial to learning, so helping students to understand why and how concepts are connected, and giving a sense of purpose, etc. Systems thinking provides personal, social, and professional relevance, so allowing students to see views or to view possible professions, and clarifying chemistry's purpose in human and social issues, as well as allowing students to make connections to their personal lives. And then we've also found that systems thinking allows perspectives to be shared and gained, which was a really interesting finding that we found from one of our studies. And then lastly, systems thinking captures interest and engagement. So if you want to, look at where these benefits stem from, I encourage you to look into those papers that I've cited in the left-hand corner. But while there may be benefits and opportunities from implementing systems thinking, there's also challenges and risks, which have been reported in the literature. So, looking back at that Menti question for those who may have implemented, you might have some unique individual views concerning the potential challenges and rewards inherent in development or implementation of curricular changes. And so to bring more awareness and to discuss these benefits and challenges, an international group of educators on the left-hand side of the screen, we have curated a list of potential challenges, which you see here as educator. They're grouped under educator profile, contextual factors, educator attitude, and educator experience. And I want to emphasize this list is not exhaustive of all the challenges one may experience. In each group, what we plan to do and what we're working on currently is creating a resource that will acknowledge these challenges, but also to provide guidance to help educators look beyond these challenges and focus on the enhanced learning outcomes results from applying a systems thinking approach. And so this was one of several resources of a website that has been created by by a working group of members of the IUPAC Systems Thinking Project. So now I'll pass it back to Peter to share more about this website.
Thank you. So a couple of URLs you might want to try to follow up on after this webinar. One is the resources at kcs.ca, but SASDICE, Sustainability and Systems Thinking in Chemistry Education. It's simply sasdice.com, and there's a QR code there to access that. This is a resource that was created by the second IUPAC working group that I mentioned. And I'm just going to give you a 30-second tour of the resource. And then Alisha is going to come back and talk about a few of the components of the resource a little bit more carefully. So on the front page are some questions about systems thinking, just a place to get started if people don't know really anything about it in terms of application to chemistry education. And then educational resources. So one of those is tools for systems thinking. And if we want to do systems thinking, mapping of systems is really important. And I'm going to show you just a little bit later on a tool that we've created at the King Center for Visualization in Science called Socket. I'm also going to show you the planetary boundaries visualization. And there are a couple of other tools that you can do to do systems thinking. Again, not complete, but a curated list. And then Alisha is going to spend some time walking through a wonderful resource on how to teach chemistry using systems thinking. So if you want to get started and you've been teaching conventionally for some time, there are little things you can do to take one topic and begin to transform it into more of a systems thinking approach. That work on barriers is getting started, as Alisha described, and we'll come back to that also. There's a glossary of terms, and here you'll find a glossary developed in conjunction with David Lewiska and the ACS Green Chemistry Institute. The key IUPAC projects focused on systems thinking and sustainability are listed here, including the two that I mentioned. We have related initiatives. There you'll see the GCTLC, Beyond Benign, the ACS GCI, KCDS, and so on. And then I think particularly useful here if you want to have an informed approach to systems thinking and connecting to sustainability. We have a set of probably now 60, 70 curated publications, and you can look at each one of them, find the reference, and a hyperlink actually to the resource, and take things further.
Great. So I'm going to share a little bit more about the development of a systems thinking educational framework, and as well as examples that were created to guide and facilitate the application of systems thinking lens in the planning, implementation, and assessments of chemistry lessons. And so you can access this framework through the main SASDICE website under educational tools, like Peter had mentioned. And the QR code here will take you directly to the Google site where the resources on the framework are provided. So next slide, please. Awesome. So this is the framework that we created. And when I say we, I want to acknowledge that this framework was driven by Vicente Talanker, who brought me on board, and that was a wonderful experience. But really, he was the main driver of this framework. And like Peter said before, the main purpose of this is really to provide a guide for educators who like to implement systems thinking, but really don't know where to start. And so this framework is composed of these three sections: planning a lesson, it could be a lesson module unit, implementing it, and then coming back to assessment throughout. So that formative and summative assessment. And each section outlines specific tasks that you see within each of these sections that are interconnected and need to be revisited in iterative ways when building, implementing, or evaluating a lesson, etc. So let's start by looking at the planning phase. And so when planning to teach chemistry using a system thinking approach, we suggest completing four tasks. The first task could be contextualizing, selecting a relevant context to anchor the instruction. Then defining the scope of the lesson by focusing in on that context. Then the next step would be creating multi-dimensional learning outcomes based off of central ideas, systems thinking skills, socio-environmental competencies, etc. And then lastly, you would build and engage, and you'll build a instructional sequence based off of those learning outcomes. So one example of a relevant socio-scientific problem could be nitrogen fixation. So human activities have significantly altered the natural nitrogen cycle, doubling the amount of fixed nitrogen in the environment. And so this has led to several ecological consequences, including greenhouse gas emissions and water pollution. So understanding the impact of nitrogen fixation can help address challenges related to biodiversity loss and climate change. So we've chosen this context, and once the context has been chosen, the next step is to find the scope of the system to focus on, because there is, as I just shared, there's lots of connections to nitrogen fixation. And so as part of this, we suggest creating a system-oriented concept map, so what we know as SOCME, to really make the different subsystems in interaction related to the problem under analysis. And so I'm going to pass it over to Peter here on how we can actually do this. And his team has created a really cool tool to help create SOCMEs.
So if you're a typical chemistry educator, you've thought about concept maps. These system-oriented concept maps are a new way that the STICE project, the Systems Thinking Projects, has been using essentially to try to zoom out from a little problem, begin to understand the system, think about the boundaries, but just expand to a more holistic view. And this is a tool on the KCVS website, and it's also linked on the tools on the SASTICE website. So let me just show you how that works. Here I have created a socket, a system map for ammonia, the example that Alisha was just talking about. And the tool is really easy to use. I'm going to zoom in just a little bit. So this, when we teach general chemistry, is typically the focus of what we do with the Haber-Bosch process. It's ammonia is made from hydrogen and nitrogen. This is the core reaction subsystem. And then we maybe have some questions about perturbing the equilibrium or the kinetics, some mathematical kinds of questions about it. But with systems thinking and with the system map, we can zoom out a little bit and start asking some questions. What are the other subsystems? Where do those hydrogen and nitrogen atoms come from? What are the energy inputs? How do we control the reaction? What's all that ammonia used for? And then what are the impacts on water, on land, and on the atmosphere? And people who use this socket tool say, hey, it's a lot of fun. It's an interactive, dynamic tool that uses force-directed graphs to locate the different subsystems. And then it's very easy to connect the subsystems and nodes within the subsystems. And so I'm going to take that one step further by showing you now what that would look like if we start asking some questions. So we ask, well, where do the nitrogen atoms come from? They come from air, but that requires energy and material. What about the hydrogen? And then the realization is that the hydrogen for the production of ammonia and for other uses is largely still on our planet coming from fossil fuels. So we're using fossil fuels to create hydrogen, to create ammonia. And that process, that single Haber-Bosch process, consumes almost 2% of the energy we use on our planet. Requires high temperature, requires specialized catalysts. We can't do it the way nitrogenase enzymes do in nature. And then we make use of that ammonia not only for things like fertilizers, but as a molecular energy carrier for refrigeration and for explosives. So we're expanding the system. And then I'll show you what a more complete SOCME would look like for that system, where we now start looking at the impacts on our various matrices in our environment. And there's no such thing as a correct SOCME. The idea here is to brainstorm, to begin to expand your system. What is it that we want to focus on? And then for a particular unit or course or topic or lesson, we can then draw some boundaries around that to get a sense of what we want to focus on. So zooming in to look at a particular part, zoom out to see more of the system, and that's really an essential feature of systems thinking.
Wonderful. Yeah. So Peter had just kind of emphasized that main point of when you've created this SOCME, or maybe there's an existing SOCME out there, and I'll point to some of the resources later on where you can find that, is that you want to identify what aspects of that system you want to focus on, and the different subsystems whose interactions will be analyzed in a chemistry lesson, class, etc. And so while after doing that, the next step is to define what learning outcomes you want students to demonstrate and take away from that lesson. And so we frame these learning outcomes under 4 categories. So meaningfully understanding central ideas in chemistry. So that's that top left corner. Applying core science and engineering practices to investigate problems and design solutions. Developing systems thinking skills to analyze the system of interest, and acting with socio-environmental responsibility. So you're creating, learning outcomes that align to these aspects. Maybe you want to just focus on one and build up over time, but it's a starting point. Okay, so if we want to look at systems thinking skills to embed, we can always come back to these 4 categories, right? So the composition, the structure, the behavior, and system effects. And so I'm not going to go into too much detail, but by identifying where some system thinking comes in, it could be defined based off of one of these 4 components. So let's look at how we could define these learning outcomes. And now I have another socio-environmental problem, ocean acidification, which is one of the examples that has been provided on that website that we created. So for the ocean acidification example, one of the central ideas for this lesson could be that chemical substances released in the atmosphere during human activities can react with water, alter its pH, and induce shifts in multiple chemical equilibria that affect living organisms. So that could be a main idea that we want students to get out from a lesson on ocean acidification. A core practice of this lesson could be analyzing data to infer patterns and correlations between the behaviors of relevant components and properties in interactive systems. One of the systems thinking skills that may be practiced in this lesson could be focused on the system composition to identify chemical composition and properties of substances in the atmosphere and hydrosphere involved in ocean acidification. And then lastly, we could, a socio-environmental competency could be focused on evaluating the environmental, economic, and social impact of human activities that could lead to ocean acidification. So these are just examples, but we did a workshop on this in Thailand, and you can create your own. You can use this as a template to create your own. Okay, so once learning outcomes are defined, the next task is really to design that instructional sequence, which is getting to that implementation phase. So you could propose a sequence of tasks that engage students in mapping out the socio-environmental problem under analysis. This is exactly what Peter had done with the ammonia example. You can then zoom into a subsystem of interest and identify those major components and their interactions. You can zoom back out, looking at subsystems holistically to analyze the relevant behaviors that emerge from interactions from chemical components, and then making those connections to other subsystems to explore the effects of the interactions between the subsystems. Okay, so to do this, we show examples of each task being presented as these let's think activities, and you'll see that throughout the resource. So mapping out could look like getting students to build a SOCME of the components of the chemical systems of ocean acidification, right? So that's the map out phase. Zooming in could then be allowing students to explore the physical interactions between atmospheric components and water in the hydrosphere at the molecular level. Zooming out could look like asking students to derive information about the directionality and extent of chemical processes once the chemical equilibrium has been discussed and understood. And then lastly, we can connect other subsystems in this example by, asking students to think about how changes in chemical equilibrium could affect marine life and human communities. And so this was one example of that was created as part of this website and this framework. But there has been other resources created by Vicente, myself, and other members of the working group. Jane in the audience created the plastics problem one. So lots of great resources out there. And what I would suggest is, if you are new to systems thinking and you might be feeling overwhelmed, or maybe are faced with some certain challenges to implementation of systems thinking in curricula, I recommend just taking one piece of the framework, one item or one activity from an example, and challenge yourself to find a way to integrate it in your class. I want to briefly touch, I know we're coming at a time soon, but briefly mention that I experienced my own challenges with implementation of green chemistry principles and systems thinking within the chemistry for engineers course. But I took one piece of the greenhouse gas and embedded it within my lecture as one activity. And it's a start, right? It's a start to building onto that in the future. Okay, so now I'm going to pass it over to Peter to share another sustainability tool that can be used to connect chemistry and sustainability using systems thinking.
Thanks, Alisha. And this will be quite brief. We are nearing the end. I want to just emphasize that when you go to the SASDICE website and you look at this framework, you're going to find the framework. Alisha and Vicente developed videos to show you how to do it. Every one of these examples actually has slides you can use in class, and it's a pretty low bar to overcome to incorporate some of these examples. So one other way to connect chemistry and sustainability using systems thinking is just to think about globally about our planet, which is fundamentally transformed by human activity. And there were a couple of seminal papers published starting in 2009 in Nature by Johan Rockström and his group at the Stockholm Resilience Center. And they are about finding signposts, identifying signposts of approaching or exceeding our safe planetary limits. So to what extent do we really need to be concerned, and to what extent can we actually quantify the extent to which human activity is taking us beyond a safe operating space, which is shown as blue for these 9 Earth system processes, toward the red, which is where we start reaching tipping points and thresholds. The 9 Earth system processes: climate change, novel entities, stratospheric ozone depletion, aerosols, ocean acidification, the biogeochemical flow of nitrogen, freshwater use, land system changes, and the loss of biodiversity. When I first read that paper in 2009 in Nature, and I looked at the control variables defined to show the progress along each of these Earth system processes, I was struck by the fact that so many of them are fundamental chemical parameters, and yet chemists really didn't seem to know about this resource. And so we took, in collaboration with Sarah Cornell, one of the architects of that planetary boundaries framework in the KCS group, we've created an interactive learning tool, which I'm just going to very briefly show you. This has been published in JChemEd 2 years ago. This is the planetary boundaries framework. And the idea is to translate that research into something that educators and others can use. And so we have the 9 Earth system processes. The stoplight metaphor for each Earth system process: we're in a region of low risk if we're below the planetary boundary. Orange is probably high risk, red is definitely high risk. And for every one of these, like climate change, the definitions of the control variables, there are 2: the concentration of carbon dioxide in our atmosphere and the change in radiative forcing since the Industrial Revolution. And one of the essential features of systems thinking is that we can look at change over time. So we built in the ability to play the planet for 125 years and see when each of these Earth system processes start moving beyond their planetary boundaries. And for a lot of them, it's in the period of the 1950s, which is the period defined as the Great Acceleration. So this is the framework. The individual Earth system processes, of course, operate as a system. And so we built another view of this called the Web of Earth System Processes, where if you want to know how climate change, again, using force-directed graphs, relates to ocean acidification, you can click on a connection, find out more about it, and explore the interconnection, can really explore the Earth as a system. And then for the International Year of Basic Sciences for Sustainable Development, we developed a third view, and the view was the result of some wonderful work by the IUPAC committee to say, if you care about sustainability, but you're teaching chemistry topics organized by topic, and you don't maybe even know very much about the Earth system processes, but I'm teaching about molecular structure and bonding. Well, let's look at that. And let's look at how we could connect that to climate change. And up comes a set of resources with key terms, learning outcomes, and interactive resources that you can use. So that's the Planetary Boundaries Framework, another tool to connect chemistry and sustainability. So we want to end with talking about tipping points. So tipping points for our planet. Maybe some of you know the work of Malcolm Gladwell, the tipping point, and the tipping point revisited. The world may seem like an immovable, implacable place, but with the slightest push in just the right place, it can be tipped. And when it comes to thinking about what human activity and the Anthropocene is doing to our planet, that's not a good thing, because we're not very far as we begin to understand the planetary systems and their levers, their feedback loops and tipping points. We're not there very far from, in some of those Earth system processes, actually causing a tip to a pretty fractured world. And so again, the Stockholm Resilience Center has some wonderful resources on visualizing those tipping points. And they suggest that there are 9 tipping elements that are active now on our planet. They call them Earth's sleeping giants. And some of these are going to be familiar to you and your students. My students didn't know anything about changes in Atlantic circulation, for instance, and some of the feedbacks that there are that are really important. Again, fundamental chemistry is involved. So those are tipping points we worry about. But in the context of this webinar, where we're saying, how can we move the community of chemistry educators toward sustainability, towards reimagining what we do so that we can achieve educational change? Educational change is very hard to do, but with the right push, with understanding the tipping points, it can be tipped. And so we think it's really important to understand the educational systems that need transformation, to identify the levers and tipping points and see whether we can use those now to get over those tipping points to where we want to be with respect to sustainability, deeply, integrally connecting chemistry education to green and sustainable chemistry. And so I want to just finish my part here with one final SOCME. And I've just been playing with this a little bit to think about if we take the barriers that Alisha was talking about, and we create a SOCME about where we want to be, and then start trying to understand the systems that we're going to have to think about. And here I haven't shown any of the interconnections, but just identifying the subsystems. So Alisha talked about educator attitude and educator profile and educator experience. And within each of those, there are various nodes that are interconnected within a system and beyond that system. But we also have to think about socioeconomic context. We have to think about executive orders and political circumstances, funding agencies, graduate outcomes, curriculum constraints, and then the chemistry department context, the institutional context in our chemistry courses. And so we're going to be suggesting in our IUPAC working group that we see if we can do some mapping of that educational system and start to understand what the key levers and tipping points are toward educational change. So let me turn this back to you, Alisha. I'll stop sharing my screen.
Yeah, so here we go. Share. Present. Oh, sorry. Technology. Okay, where are we? This one. And present. Oh, now I just need to get to. No, I'm gonna. I had this all set up. There we go. Present. No.
There's a different present
Yeah.
button for start from this slide.
Yeah, present.
It's down at the bottom usually.
Oh yeah, here we go. Let's try that.
There we go.
Yes, thank you, Peter. Okay, so I just want to make a note of the many other resources that are available to the educational communities to learn more about systems thinking and sustainability. And I want to highlight that the green chemistry teaching and learning community at Beyond Benign is a great space for community members to ask questions in the forums, share resources, and there's a really cool feature that's soon to be launched, which is our groups. These groups are going to be spaces on the GCTLC for registered users to connect, network, collaborate, share, and learn together. And so we're currently in this soft launch period. And we're starting to create limited groups to really test out the functionality before they become live June 1st. And so we are creating, I'll be creating a systems thinking group. And so if you would like to be part of this soft launch and test it out or preview time, please email me at my GC, it's right on the screen there, if you're interested in joining that systems thinking group, and we can start talking about systems thinking, sharing resources, etc. And then another really great resource has been created by the American Chemical Society Green Chemistry Institute, where they've created some learning modules to draw connections between green and sustainable chemistry and systems thinking, and then highlighting how those ideas connect to the current chemistry curriculum. So you can find these resources. They're on the SASDICE website to learn more. And so we want to thank you all for listening to our presentation. There's a bunch of QR codes here that we presented throughout, but coming back to the SASDICE website, the framework, there was an article we published on the framework, and then there's YouTube channels that complement some of the resources there. So to now getting into our kind of discussion phase of the presentation, we're gonna do instead of ask me anything, we're gonna do ask us anything. Do how's our time for that right now?
Yes. So I just want to ask, just based on the time, we are running behind. But we were wondering if it was okay if we just add you to another breakout room later. So then we'll just have
Sure.
all the speakers at the end have their breakout rooms, and everybody can go to the ones that they want.
And
that
if
works.
people can get this QR code, then they could drop some questions they have into the Menti, and then we could come back to them in the breakout room. That would be great.
Exactly. So if people want to, they can scan right now, and then we'll go for a break for 5 minutes, and we'll come back and start with the second round of talks. And at the very end, we'll have breakout rooms for everybody.
Okay, great.